All right, welcome to part 2 of the measurement study session with Schmidt series. All right, part 1 I put on Google Classroom. You should see that. It's a measurement video as far as using a ruler. Be sure to look at part 1. Part 1 is very necessary component of the test. So what we're looking at here is part of the test. And so I have created the test, and I just want to go over certain things. So one of the things that we are going to be looking at is accuracy and precision. So accuracy and precision. So you need to make sure you understand the terms and you can differentiate between them. Accuracy is a measure of how close a measurement comes to the actual or true value of whatever is measured, and precision is a measure of how close a series or multiple measurements are to one another. So if I have some trials, all right, and I have trial 1, let me put this in here, trial 1, 2, and 3, and let's say I was taking the density of aluminum, all right? I know that's hard to read. Maybe I should make that a little easier to read. Let me fix this pen. Yeah, that's about as good as it gets, guys. Density of aluminum. All right, and I did a trial where I got, let's say I got 5.3 grams per cubic centimeter, and I got 3.1 grams per cubic centimeter, and I got 2.0 grams per cubic centimeter. How would you describe my results if you went to a reliable source like the Handbook of Chemistry and saw that the actual value for the density of aluminum is 2.71 grams per milliliter or 2.71 grams per cubic centimeter? How would you describe that? Could you describe that as accurate, precise, accurate and precise, neither accurate or precise? Which one could we use there? Neither. So why would you say neither? So let's look at accuracy. Accuracy is a measure of how close the measurement comes to the true value. If the true value is 2.71 grams per cubic centimeter, are any of these values close to 2.71? 3.1? Okay, you can say that's close, but oh, trial 3 you think is closest? Actually, 3.1 is closer. Yeah, the 3.1 is closer than the 2.7. But yeah, but none of them are really close to 2.7, are they? So we would say it is not accurate, right? In this case, not accurate. But what can we say about precise? Precision says a measure is a measure of how close a series of measurements are to one another. Are our measurements close to one another? Is 5.3 close to 3.1? Is 3.1 close to 2? No, they're not close to one another, right? So it is not precise, right? You see that? So you have to interpret your results sometimes. And so you're going to have to tell tomorrow whether something is accurate or precise, and that's how you're going to do that. So let's use another example. I'm going to get rid of that. You say, man, can I go back and I didn't quite get that, Mr. Schmidt. Guess what? Just rewind. Okay, just rewind. All right, it's all good. Be kind. All right, let's try another one. Let's say we get 2.70 grams per cubic centimeter, 2.71 grams per cubic centimeter, and 2.70 grams per cubic centimeter. What can I say about my results? So let's look at accuracy, which is a measurement of how close the measurement comes to the true value. If we look at our results, are they close to the true value of 2.71? Yes. So what does that tell you about the accuracy? Yeah, that it's accurate. So it is accurate. And then What do we see about our measurements? Are they close to one another? 2.70 is really close to 2.71, and 2.71 and 2.70 is really close to 2.71, right? So they're close to one another. So they are what? Precise. So this in this case, they're accurate and precise. You see that? Okay, let's try another one. Zip, 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 zip. Zip, 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 zip. Okay. Let's try this. Let's try, whoops. 3.5 grams per cubic centimeter. 3.5 grams per cubic centimeter. And 3.5 grams per cubic centimeter. All right. So what do we notice about this? Are our results accurate? Are they close to the true value? No, they're not. So they are not accurate. Are our values close to one another? Yes. So what are we going to say about that? They are precise. So not accurate, but they are precise. Do you see the difference between those? So I use those in about every way that I can use those. All right. So if you can recognize that for the test, then you're going to be in really good shape. All right. So what if I use this last scenario and I said, calculate, or what is the error? Y'all know what the error is? How do we get error? Y'all have that in your handy dandy notebook? What's the formula for error? Yeah, that's right. Error. Somehow I have a hard time with that. Error is equal to you said the experimental value. That's right. Experimental value minus the accepted value. Now, in this case, what is the experimental value? Yeah, you see, in this case, we can say that if we took an average of all three trials, what would our average be? It would be 3.5, right? You can say that your experimental value, if you took the average of that, is 3.5, right? Yes. Yes, you would have to take the average. So it'd be 3.5 grams per cubic centimeter minus what's the accepted value, which is 2.71 grams per cubic centimeter. I hope all of us have our calculators out, and we are calculating this. If you don't want to be doing this the first time tomorrow, that's not good. So try this now. Even for you at home, try this now. All right. Even for you in class 6 hour, try this now. So let's say 3.5 minus 2.71. And we get what? 0.79 grams per cubic centimeter. That's our error. So that's all you have to do if you're asked to calculate error on your test, right? Just know that formula. All right. What is the percent error? What is the formula for percent error? Percent error is equal to, who said this? Yeah, the absolute value of the error over what? Accepted value, which I'm going to put as AV, just so you know that's what I'm abbreviating, times what? Okay, I'm not going to put the percent sign in there because I did not realize on your calculator that y'all can put in 100%. And when you do that, it does not give you the right value. So just in your calculator, only type in times 100. Okay, and that's going to give you the percentage. All right, so in your error, you just simply fill in what you have. It is 0.79 grams per cubic centimeter divided by, what is the accepted value? 2.71 grams per cubic centimeter. and then multiply that times 100. And I'm going to move the screen up a little bit. All right. And so what do we get when we do this? Divided by... What'd y'all get? That's right. I don't know. My calculator needs light, evidently. You said 29.15, and we'll go with that percent. All right. Any issues there on calculating error and percent error and understanding whether results are accurate or precise? Do you think you can determine what the experimental value is in a lab scenario? Where are you going to find your experimental value? Yeah, it's going to be in a chart. That's where your lab results are reported, right? Where are you going to find your accepted value? Now, some reliable source, and it will say it was in a data table or it was something like this. It's a reliable source, all right? So make sure you're looking for that. All right, it's a given. All right, all right. In this whole series, I use aluminum for the whole thing because I just wanted to stick with one. It doesn't mean that we're using aluminum tomorrow. Okay. So the next thing, make sure you go and watch part 1, the measurement series study session with Schmidt. That's going to be very helpful for you. Okay, let's look at this. We did some lab stuff. Y'all remember doing this? I need y'all to help me out. I didn't want to just plug values in here. I wanted y'all to help me out. So this would just be organic and work. So just give me a mass of an empty graduated cylinder. Give me what would be a good mass. Say again. 120, 120.4 grams. Let's go with it. 120.4 grams. Yes, it is, but that's what he chose. All right, and actually I don't need to have the unit in here since I have the unit expressed right here. Do you see that? 120.4. Now give me the mass of the graduated cylinder with a liquid. You want to say 120? It only went 1 gram? I like that. 130.4. I think we're having a battle in here. That's all right. All right. Now, what if I asked you, what is the mass of the liquid? Yeah, you do. All right. Oh, by the way, before we finish this, we're just making these values up. What volume do you want the liquid to be? 20? That's exactly what we used on the test. Not on the test, but in our lab, right? We use that. So 20 cubic centimeter. All right, so now we want to find the mass of the liquid. You'll understand I'm just making these values up. These right here, and these right here, and these right here. They will be given to you in a test type scenario. All right? But just for the sake of this study session, we're just making up values. All right, so how are we going to get the mass of the liquid? Mass of the liquid is equal to mass of graduated cylinder with liquid, right? Minus empty graduated cylinder, GC, right? Anyone have a problem with that? Yeah, I know you can't read my writing, but you can hear what I say. All right, and you can also put on the subtitles, and then you can read it. Okay, so what's the mass of the graduated cylinder with the liquid? 130.4 grams. What's the mass of the empty graduated cylinder? 120.4 grams. What's the mass of the liquid? 10 grams. Do you see that? So that's an easy little scenario. Definitely will be on your test, 10 grams. And I don't have to put the unit in there because it's expressed right here. I could just say 10. Now, I asked you, what is the density? Do you have everything you need to get the density? Yeah. For density, you just need the density of the liquid. This should say of the liquid. You have density is equal to mass over volume. What is the mass? 10 grams. What's the volume? 20 cubic centimeters. And what's 10 divided by 20? Y'all made an easy scenario. No, 10 divided by 20 is not 2. It's, put it in your calculator. Everyone put that in your calculator. Do you know that 10 is half of 20? Yeah, it's 0.5. Okay, so 0.5 grams per cubic centimeter. You see how easy that was? Those are easy numbers. Well, if they're not easy numbers, you still know what to plug in your calculator, right? Yeah, so that's the idea there. Okay, so let's go to another scenario. I already have these data tables made. This is really nice. And so here, we're going to make up some fictitious values for mass, initial volume, and final volume. By the way, before we start, what does the word initial mean? Yeah, it means at the beginning, or yeah, you can say when you start. You can say at the beginning, right? What do you know about initials? You have initials for your name, and what are the initials for your name? They are the first letter of your name. Do you see that? So another way of saying it is first. All right, and y'all probably know what final means, right? What does final mean? Final means last. Okay, so that's very important that you understand those words. I had first hour was having an issue with understanding what initial means, so that's why we're spelling it out right here. But it means start, beginning, or first. All right. So let's come up with a mass. Y'all give me a value. 2.4 is what I heard. 2.4 grams. And I have one of my students over there in the corner saying that doesn't look like a 4. I can already hear it. So before it comes out of her mouth, I'll fix it. Give me an initial volume. 88.7. It's my favorite radio station. 88.7. And then what's my final volume? You want to say 90? Okay. And I'm probably not expressing this lab very well, but this is where we did the mass of the metal. Y'all remember this? This is my graduated cylinder because I don't draw very well. And so we have different values, right? And so here we have an initial volume, right? And then we put in the metal, right? And when we put in the metal, here's the metal piece. Metal. What happened to the volume of the water? It rose. And so the difference in the volumes is going to be the volume of the metal, right? And that's what this data table is telling us, all right? We have an initial volume, and then we have a final volume, and then from that we can figure out what the volume of the solid is. Do you see that? So that's exactly what we're looking at. So let's first figure out what is the volume of the solid. So volume of the solid is what? Volume of solid. How are we going to figure this out? Yeah, you're going to subtract final volume minus initial volume. Yes, you need to know this for your test. I'm not going to give you any formulas. So what's my final volume? I'm going to go ahead and put a 0 on this. No, my final volume is 90.0 milliliters. Read your table. No, that's your volume of the solid. So that's what we're trying to find. All right. So what's the initial volume? 88.7. So what's my volume of the solid? 90 minus 88.7. You're going to say it's 1.3. So here we can say this is 1.3 milliliters. So what we would see, even though we don't necessarily see it right here, is the change in volume is 1.3 milliliters. All right, if we were going to watch the water level rise, it rose by 1.3 milliliters. All right, now, what is the density? How do I get density from this? Density is what formula? Mass over volume. Do I know the mass? Yeah, it's 2.4 grams. I'm looking at my data table right here. What's my volume? We calculated, by the way. Yeah, 1.3 milliliters. And then all I do is take 2.4 divided by 1.3. And what do I get? 1.846 grams per milliliter. And if I were going to consider sig figs, I could do that, right? All right. There's a couple of them that ask you about sig figs, but I'm going to address that in another area. Okay, are we good on that? You should be good on that. So what if I wanted to identify this substance? What would I have to do? I find a density table, and then I compare 18.4 to whatever I have on a density table. If I find another substance with that density, then I can say it might be that substance. You see that? All right, we did that in bell work, week 7, day 1. You can go back and watch that if you didn't understand that concept that I just brought out, because I don't have time to go over it in this video. All right, the last part is we have some conversions. Are y'all ready for some conversions? All right, let's come up with a good conversion. Let's use something that we know a lot about, and that's time. All right, we're gonna use something we know about, and I didn't write anything out. Y'all give me something in seconds. Give me a value in seconds. 33 seconds. 33 seconds is blank number of years. You see that? Let's figure that out. 33 seconds is blank number of years. So do we know conversion factors for time? Yeah, you should. Now on your test, you will have conversion factors given to you. They'll be in a table. All you have to do is find them. You see that? But I don't have a table to show here, so all we're going to use is something we know. So what are we going to start our bracket with? 33 seconds. What goes in the bottom of the bracket? Seconds. What can you convert seconds to? Minutes. All right. And how many seconds? 60 seconds equals 1 minute. Are we at years yet? No. So what can we do? We keep going. This is going to become what? No. What unit is here? Minutes. And what are we going to put here? Minutes. You see how the unit's the same? And you can go minutes to what? Hours. Yeah, and you can say 60 minutes is equal to 1 hour. Now what unit goes down here? Hour. Now y'all getting it. Now y'all getting this. Hour to what? Day. How many hours? 24. How many days? 1. And then what unit goes down here? Day to what? Year. 1 day. No, not 1 day. How many days are in a year? 365 days is 1 year. Now all we have to do is do the calculation, and we are going to be in years. So you're going to take, guys, what you can do is you can multiply everything on the bottom and get that value and then divide it into 33, or you can take 33 divided by 60 equals, divided by 60 equals, divided by 24 equals, divided by 365 equals, however you want to do that. But let's see if we get the right answer. Everyone do this together. So let's see if we get the right answer. I got something like 0.00000 1046. Is that what y'all got? Yeah. How many sig figs can I have in my answer? 2. So we're going to look at sig figs here. What do we know about these zeros right here? What kind of zeros are those? Do those count? No, leading never count. So we're going to start at the 1. 1, 2. When we look at this 4, is that 4 greater than 5? No. So what are we going to do? Yeah, we're going to keep it as 0.0000010, right? Years. And how else could we express this? Scientific notation could be 1.0 times 10 to the what? How many times did we move the decimal to get to 1.0? 1, 2, 3, 4, 5, 6. So we're going to say to the 6, but it's got to be -6 because this number right here is less than 1. So that's another way of expressing that. All right, do we know about our types of zeros? We understand the rules for counting significant figures. If you don't, make sure you watch a video under Schmidt Specials about counting significant figures. This is going to wrap up the Schmidt Studies series, part 2. It was the last part of the series. I appreciate you tuning in. Please tell your friends. And yeah, if you want to, watch it again. I know I will. All right. Thank you for watching.